All right, let's start the recording. And just remember where we were. We were dealing with transformations last time. And yeah, wow, no space. Maybe I have plenty of space and too much stuff. Maybe that's what it is. All right. Oh, good, Stephen. Thank you. Thank you. I was going to actually ask. Stephen had a problem with Alex. So if anybody else runs into anything, if you run into anything where it says you're a guest or you don't have an account, let me know, and we can fix it. All right. So last time we talked about vertical translations, horizontal translations, vertical reflections, and horizontal reflections, and then vertical stretching and shifting. Stretching and compressing. Stretching means you pull it out farther. Compressing means you push it in farther. We got into it, and we were told to follow this order of which one of these should I do first, second, third, forced. That's not even a word. The horizontal shift first, horizontal vertical stretch and shrink second, reflections across the X and Y axis third, and then the vertical translation up or down, and that's last. So here is this idea or this concept of here's where A, B, H, and K live on any function that you get. There's technically, like here's f of x. These are unique for each specific function. So for instance, if I come up here and just consider this quadratic, because this is really the one that everything starts to show up. Here's my basic f of x is equal to x squared. And then we talked about where is A, where is B, where is H, and where is K. So here's the idea that x squared can be rewritten as A is on the outside, A times the inside is the x squared, right? Well, on the inside, that B is the coefficient of the x I started with, and then minus H is the squared plus K. Each one of these has this concept. So remember, B and H are impacting X, A and K are impacting Y. So this is the idea. This is where they live for this function. For the cube, it's really no different. It's not that different, right? It's that exact same thing, but now this is a cube. For a square root, what does it look like? Okay, same idea, outside. Inside is what's under the root. And then outside plus K. So this is what f of x looks like if we kind of jot down all of those A, B, H, and K. You can see how they live naturally in our problems, right? But I want you to understand they're the same. The concept is the same, but they are different for each function. It's not always going to be exactly the same. So when I say messes with the inside, it's really easy to see what that looks like for a quadratic function, a power function, or a root function. Inside means under the root. Outside means outside of the square or outside of the root. So it's not as easy to see with linear equations, but once you have a second power or some kind of a power, it becomes a lot easier to deal with. All right, so we looked at translations, and we talked about them in terms of moving left and right, moving up and down, and then also kind of converted that to, if I'm going to shift right 1 unit, that means H needs to be 1. If I'm going to shift down 4 units, that means K needs to be -4. And then H affects X, K affects Y, so we make those changes to our coordinates. So the next page, we were told to graph the function h of x is equal to 1/3 x. We were told to do a bunch of stuff. So here are the two. There's the base unit, or the base graph is the green one. And then what did we do? We went left 2 and then down 5. And that put us, the graph doesn't change shape. It just moves, right? It's got the same rate of change. And then we're given x squared. Then we're told to do 3x squared. And then below that, we're told to do 1/3 x squared. So x squared gave us the parabola we're used to. 3x squared is a lot steeper. And then when I do 1/3 out front, that means that I'm going to do what? This is going to be a horizontal compression or shrink . So what does that mean? That means if A is 1/3, now when I plug in, for instance, 0, what happens? I get 1/3 times 0 squared, which is 0 times 1/3, which is just 0. That one doesn't change. How about at 1? It's 1/3 times 1, which is 1/3. So I've got my 0, 0, but now when I go out to 1, I only go up to 1/3. Don't do that again. That's right there. If I go to 2, what's going to happen? Really, 2 is not that interesting because I'm just going to get more fractions. Let's go on to 3. Because 3 times 1/3 is going to give me 1. So I've got to go all the way out to 3 to get to 1. So what have I done? This is what my graph looks like now. And it's symmetric. I know I'm doing a terrible job drawing here. Yeah, we're going to go out here. So I said compression and I got ahead of myself. A lot of people talking. Ooh, oh, forgot the square. You're right. That's okay. Thank you. Man, you are on it today. I love it. 1 squared is 1. That one's fine. 3 squared is 9 times. Okay, so now I go up to 3. So at 0, 0, I'm fine. At 1, 1/3, I'm fine. But then at 3, I'm at 3. 1/3 and 3. So I look like this. Okay. If I want to do it justice, and let's try to do that. Let's look at this in Desmos. And I want you to see y equals f of x. Equals x squared. Okay. Y equals 3x squared. And then y equals 1/3 x squared. So there you go. Root function is the square, right? And then what happens when a, that number on the outside, when a is larger than 1, what do? I get a, it's a horizontal compression, which is a vertical stretch, right? I pull up, and that makes the parabola steeper. As you can see them both ways. The higher number compresses. Yes, the higher number is going to compress this horizontally or stretch it vertically. Both of those concepts are correct. Since you're messing with the outside, that means you're messing with y, so you're messing with the vertical. So you're right, we should say, when I'm looking at y equals 3x squared, I'm taking and I'm doing a vertical stretch. So I'm pulling it up, and then when I do it, when a is less than, or it was between 0 and 1, or negative, absolute values between 0 and 1, I compress. So I take the original function and I smash it down so that now the parabola is wider. So let's write that correctly. First, let's get that right in our notes. So we're going to label this as a vertical stretch by a factor of 3. Okay. The higher the factor, the more steep the growth, or the more steep the stretch. And then for the one below, we're going to call it a vertical compression by a factor of 1/3. All right, again, my drawings are not great. I should probably, if I were a smart person, I would bring this into the notes. So let's do that. And now we can see them and compare the 3. All right, so the colors match up and everything. So, yeah. So questions on that? I've upset the word gods by doing that. There we go. All right. Good. All right, so we're making sense. That's what we want. That's the goal. So we dealt with these. Last one from 1-6. And, we have to remember to state in a phrase. That's a good question, Andrew. I think come back to that page 2 right here. Up, down, left, or right is always a shift. And then you have reflections, which is where you reflect across the x-axis or the y-axis. And then stretching and compressing is where we what we call what's going on there. So shift, up, down, left, right, reflection across the x-axis, reflection across the y-axis, and then stretching and compressing. Stretching, so we have it here in the notes. If I've got y equals f of x, then y equals a times f of x, right? I've manipulated the outside as a vertical stretch or compression in the amount of a that affects the y-axis. What does that do? When I do that vertical stretch, what have I done? I'm multiplying y by whatever the number is up front. So I take my original function and then I stretch it until my function now matches this idea. So whatever my output was in the example I had, what did this do when I multiplied by 3? It stretched by a factor of 3. What happened when I did a 1/3 there? I would compress by a factor of 1/3. So yeah, vertical stretch by a factor of 3, vertical compression by a factor of 1/3. And then if I want to manipulate this on the inside, what does that look like? That looks like 2x squared. Okay, what did I do there? Now I'm on the inside. I tell you what, let's make it more noticeable here. And notice I'm being very careful with the parentheses here. All right, what have I done? On the previous two, I multiplied on the inside, or excuse me, I multiplied on the outside by 3 1/3. That gave me the vertical stretch, vertical compression. Now I've done the same thing, multiplied by 3, but now I've done it on the inside in both cases. So I multiply by 3 on the inside, and what happens? I get that vertical stretch. When I multiply by 1/3 on the inside, I get that vertical, excuse me, I did it backwards again. There we go. Yep, horizontal, you're exactly right. So 3x all squared takes the red graph and compresses it. So when I have, so just like what we're used to with H and K, if it's on the outside, it does what it looks like it does. If it's on the inside, it's reversed, right? If I've got plus K on the outside, that means I'm moving up units. If I got -4 on the outside, I move down. On the inside, if I have a +4, that means I move left 4. If I have it on the -3 on the inside, it means I move right 3. So that idea is the same. I've manipulated the inside, so this is going to be a horizontal stretch or compression. Which one is it? Well, the red is my original, and the purple is my new. Does that match up with what we did? Look at that horizontally. Horizontally, that's a compression, right? I've pushed the sides of that parabola in. So when I'm multiplying on the inside by something greater than 1, I'm looking at a horizontal compression. And when I multiply on the inside by something between 0 and 1, I get a vertical stretch. Okay. It's nice that it stays consistent. It's always, if you manipulate the inside, it does or the outside, it does exactly what it looks like it would. If you manipulate the inside, it's always the reverse idea. You would think multiplying the inside by 3, make it larger, would make a cause it to rise up. It's horizontally, we would think it would cause it to stretch, but it doesn't. It causes it to compress. And then the 1/3 on the inside there causes, instead of it to horizontally stretch, it actually compresses it. Set it backwards to compress the stretches. Anyway, all right, so that's the idea here. All right, so let's keep going. And see what this last one does. All right, so here is a graph. Once again, I don't have the formula, I don't have the equation. I don't know what this is, I just have a graph. I'm told in the graph that this is y equals f of x, so this is a function. And they give us two graphs and they ask us to show what they would look like. And those graphs are y is equal to negative f of x and y is equal to f at negative x. All right, now let's take a look at my function. I have 3 points, right? So I have the point 4, 1. I have the point 2, 3. And I have the point -1, 0. In there. So instead of trying to get an idea of what's happening, you're trying to, am I stretching, am I compressing, am I flipping, what am I doing? I'm just going to apply what happened directly to these points, just like we did in the last class. So if I have y is equal to negative f of x, am I multiplying y by -1 or x by -1? Which one is that doing mathematically? Y by -1 or x by -1? Okay, so it's on the outside, so remember what that means. Right, that means I multiplied y by -1. So that means 4, 1 becomes 4, -4. 2, 3 becomes is everybody cool if I just write 2, -3 and then -1, 0. becomes -1, 0. That one doesn't change. Oh, that's okay. So now where are my points? 4, -4. Or -1. Yes. Oh my goodness. -1 times 1 is -4. What is going on today? All right, let's get it right. Back this truck up. Thank you. All right, 4, -1. Go out 4, down 1. Here I am. Second point, go right 2, go down 3. And then the last one stayed in the same place. If I can plot those 3 and I know what's connecting them are straight lines, that's never going to change. If straight lines connect, whenever you're given the original, then straight lines are going to connect at the end. They'll just be shorter or longer than usual. All right, and then we have, whoa, don't do that. I just got it where I wanted it. All right, and then we have this one. Okay, and what did it do? What was the result here? Right, what I'm doing is I'm showing you how you can manipulate this algebraically, and then you still end up with exactly what we thought would happen. When I multiply the outside by -1, I've got a, which kind of a flip do I rotate over the x-axis or over the y-axis? Which one did this do? This went across the x-axis. So this is a reflection across the x-axis. Good. Reflect across x-axis. So guess what the other one's going to do? It's going to reflect across the y-axis. So I start out with 4, 1, 2, 3, -1, 0. And what happens in this one? The inside is negative, so that was B is now -1. So that changes 4, 1 to -4. That changes 2, 3 to -2, 3. And that changes -1, 0 to 1, 0. All 3 of these move. -4, 1 is going to put me here. -2, no, try that again, Larry. -4, 1 is going to bring me over here and then up. -2, 3 is going to be left to up 3. And then -1, 0 becomes 1, 0, which is right here. There again, if I connect these with straight lines, which is what I am supposed to do, I get, you see the graph, and it is a reflection across the y-axis. Right? And you can even see, you can start to see the manipulation here, how 4, 1 becomes -4, 1. You see how this rotated right across that y-axis. Okay. So that's the idea. And that's 1/6. Let's tackle this last transformation down here. These transformations to graph this function. I got a couple of things going on here. My order of operation tells me to do what first? Let's go back and look. Horizontal shift first, horizontal stretch and shrink second. Let's just copy this over. It's just always good to have on hand, especially when we're working these problems. Probably something for the test you're going to want to have written down on your cheat, on your little notes. So what have I done here? Well, let's start out with what do I have? The base or the mother function here is y is equal to the absolute value of x. Okay. Now, what does that turn into when I put in all the a, b, h, and k? Okay. The translated looks like y is equal to a is on the outside, b times x minus h plus k. Okay. So now that you can see that, what have I got here? What's doing what? Horizontal translation first. Horizontal translation is h, right? Horizontal translation is just horizontal shift. Okay. What is h in this one? First step, h is 2. Now look at it. On the inside, this looks like h is -2, but remember my general form here has a minus inside. So whatever's on the inside is backwards. If h is 2, this means go right 2 units. That's the first step. Second step, horizontal and vertical stretch and shrink. I do not have a horizontal stretch or shrink because b is 0. But I do have a vertical, right? I have a vertical stretch or shrink because right out here, a is -3. Now I'm going to ignore the negative part for a second. All right. So since a is 3, this means what? I'm messing with the outside, so this is going to be a horizontal stretch of 3 units. Ignore the negative for a minute. And then that negative is what causes the next piece. Negative. And I'm actually going to write it differently because a is less than 0. All right, since a is negative, what does that do? I'm multiplying on the outside. So what used to be 1, an output of 1 is now an output of -1. What used to be 3 is now an output of -3. I have a flip over the x-axis. And that's all because outside is negative. Okay? And then the last step is k is -4. So this means I'm going to go left 4 units. So let's start with our base function here. Y is equal to the absolute value of x. So when 0 and 0 are there. When x is 1, it's 1. When x is 2, it's 2. When x is 3, it's 3. When x is -1, I get 1. -2, I get 2. -3, I get 3. And this is it's just a v, right? This is what it turns out to be. That base function looks just like that. And it does go on forever in both directions. So we'll add the little arrows on the end. So what have we done to this problem? Okay. Well, I take the graph, I move it right 2 units, I stretch it 3 units, I flip it over the x-axis, and then I go left 4 units. That is going to take some major manipulation. Okay? So instead of trying to do this all on the graph, I'm going to take advantage of the fact that I can do all of these steps to the points. Right? So if I start out with the origin, which makes sense, right? If I start out with 0, 0, step 1 says h is 2. H is 2 means I go right 2 units. So that means 0, 0 becomes 0, 2. Next, A is -3. This is gonna take, we're gonna do this in 2 steps, or in 1 step. A is -3, that's manipulating the outside. So that means I now have the point 0, -6. And then the last step is K is -4. So that means go left 4 units. What am I? Why? Why? Dang it, Larry. Damn. All right. So let's try that again. H is on the inside. It is manipulating X. So in H2, I go from 0, 0 to 2, 0. That's that shift right 2 units. Now, get it right. A is -3. It doesn't impact this one because that multiplies by the Y, but the Y is 0. So that stays where it is for now. And then A is negative, and it's negative, it's 3, so that was handled all in 1 step there. So the last thing is K is -4. That means go down 4 units. I'm currently at 2, 0. To go down 4 units, I need to do -4 on the outside, which means I now, my origin now resides at the point 2, -4. So now I'm here. Now let's go get another one, and this one's going to make a bit more sense because I have 1, 1 here. So first step, H is 2, that's a shift to the right by 2 units. So I'll go from 1, 1 to 3, 1. A is -3, that's impacting the Y. So that means I've got 3, -3, because 1 times -3 is -3. And then K is -4. That is going to manipulate my Y value by 4 units. I'm going to go down 4 units, so now I live at 3, -7. 3, -7 is here. How are we feeling about that? Sorry about the confusion there at the first one. But if this is, so I have my parent function here is the absolute value. So if it looks like this, and I told you it's going to remain, it's going to remain or contain its original shape. Like if I have points and they're connected by straight lines, those points will continue to be connected by straight lines. So let me get -1, -1, or a point to the left, -1, 1. H is 2. That means move to the right 2 units. So I'm at -1. It means I go over to 1. A is -3. So now I'm at 1, -3. And then K is -4. So that means I go 1, -7. 1, -7 is here. And then let's see if our manipulation holds. Okay. So does this transformed graph look somewhat like our original? Still got that V relationship, but look at all the things that happened to it. It got moved right 2 units. It got stretched 3 units. It was flipped over the x-axis, and then it was moved down 4. So the flip made it point down. the stretch narrowed it, right? The stretch compressed it. Okay. Horizontal compression. What is, all right. I just got done saying. All right. So, just an off day today. Why would it be vertical? Tell me. Yes, very good. Very good. So I have A, it is on the outside. It is manipulating Y. So this is a vertical. And then if it's a vertical, what's happening here? That is a vertical stretch by factor of 3. Yes, very good. Very good. All right. So what should you learn from this? The more steps there are, the more confusing this can get. And even people that know what they're doing make mistakes. So it means you've got to practice, just like I have to practice, just like everybody has to practice with these. All right. And again, these problems weren't hard when we had all of this written for us right here, right? I was doing these problems without this on the screen, so I couldn't just refer back. You will always be able to refer back if you use these notes on the test, right? So if you make your sheet so that you can have it on the test, I would definitely put those on it. All right, let's get out of 1.6 so I stop being so silly and jump over to 1.7. All right, so I got 6 graphs here, and 1.7 has 2 parts, so this is going to feel long, but don't let it spook you here. Here are some graphs, and the question is, do they have some kind of symmetry? Okay. Do all of these look like they have some kind of symmetry? So, and when I say all of these, I mean these top 3. All right. What do we see? Yeah, I see some similarity there, right? If I imagine this as a book, imagine the y-axis as the spine of a book, and I flip the pages, won't the right side lay right on top of the left side? Does that make sense? So it looks like I have symmetry about, yeah, there we go. Yeah, this looks like symmetry about the y-axis. All right, if I fold one side over the y-axis onto the other, it'll lay right on top. Right? Or if I take the entire graph and I flip it, if I rotate left and right side across the y-axis, I'll end up with the same graph. How would you write, or how would you talk about the points of this graph? So if I have a point that is xy on the graph, then the point negative x blank is also on the graph. So let's go into some of these and let's find some nice points that are easy to manipulate. We don't want to pick points on the y-axis because that's where our symmetry is about. So if you start with a point on the y-axis, it's actually going to stay there. So instead of that, let's come over here to, I'm going to call that 8, 0. 8, 0 is on here. So that means, remember the idea is I can flip this across the y-axis. So if 8, 0 is on here, and guess what else is on here? Negative 8, 0. If 8, 0 is on here and I have symmetry about the y-axis, I gotta have negative 8, 0 as well. And that's going to go for every one of these, right? If this point is here, then its partner on the other side has to be in there as well. So the point, the symmetry looks like this. If I start out with xy, I know I must have negative xy as well. All right, so that's symmetry about the y-axis. Okay. What do you think is going to happen with the other? Okay. Now this one's not as easy, right? Because our first thought is, oh, well, if you have symmetry, if one of these has symmetry about the y-axis, then the other one has to have symmetry about the x-axis. Here's the problem. If I have symmetry about the x-axis, so let's just pretend, if I had this point, I would need to have that same point down here. If both those points are on the function or on the graph, it's not a function, right? So I can have symmetry about the y-axis, and then the other way is to have symmetry about the origin. What does that mean? Well, it means if I take this graph and I rotate it 180 degrees, I'll end up with the exact same graph. Okay? You could also see it as if I fold over the x-axis and then over the y-axis, I'll lay right on top of myself, right? If I take this second graph here, fold it over the x-axis, then I have symmetry about the y-axis, so then I fold over the y-axis. So symmetry about the origin pretty much just means if you rotate the graph 180 degrees, you have the same graph. In order for that to work, if I have points up here in the positive xy, I've got to have points down here in this quadrant. How are they different? This is positive xy, this is negative x, negative y. So if I have a point xy, I also have the point negative x, negative y. Okay? So that's the idea. It's going to make sense after we do some problems. All right. I'm going to skip this for a second because I don't really want to mess with the piecewise function at this point. I'd really like to ignore it if I can. And let's go over here and take a look at this graph. So I want you to take 1 minute. I'm going to step away, take a minute, see if you can make sense of what this is asking. Okay? We want to do 3 different highlighting styles. We want to talk about where is this increasing, decreasing, and constant, and then what's the max value and what's the minimum value. All right, I'll be right back. If you have any questions, pop them in while we're on the little break here, and I'll answer them.
Sounds good to me. I'm learning about the stretching and the y-axis. Stretch my y.
All right. So, I'm a little off today, so This is Fred. See, Fred? Fred loves math.
No, he doesn't. That's a lie.
Fred
That is a
loves
lie.
math.
That's
And that
not
is-
true.
And that is my wife. This is Fred. Fred will make you happy. All right.
Fred does not love math.
Just
Don't let him
fake-
bully you, Fred.
He's been sitting here the whole time, hasn't moved one bit. All right, so hopefully that will distract you from the terribleness of this lecture so far, and you can forgive me for not being on it today. Yes, Fred is very chill, except we got a dog 2.5 weeks ago, and the dog is not chill because the dog is a puppy. But if I make another big mistake in the notes, I'll show you the dog. All right. Yeah. Yeah. Then I'm gonna go start teaching English. He's just like, this math isn't for me. All right. So I have a graph here. I want to talk about where is this graph increasing, decreasing, and constant. I want to talk about minimum and a maximum value for it. And I want to talk about where they located. So here's the thing. The definition for increasing and decreasing is going to show up later in this section. Okay? It's actually down here on this next to last page. So this is what I want you thinking about as we tackle this problem. Okay. I didn't show you this before because I didn't want to cloud your judgment. I didn't want to mess you up. So when I look at a function, I know this is a function because it passes the vertical line test, right? You cannot draw a vertical line and hit it twice. I know these 2 points here are a little funky. They're pretty steep. They're askew, but they are this is a valid function. It passes the vertical line test. You can't hit it twice with a vertical line. So where is this increasing? Okay, I'm gonna use my highlighter to highlight the places where it's increasing. Well, increasing for us means it's going up, okay? And we read from left to right. So over here, not increasing. Not increasing is the opposite of increasing here. And then I make this little place where I jump up. That's increasing, okay? I start to go down again, and then I get to the bottom, and then what do? I start to increase. So it looks like everywhere in green is the increase. Make sense? -3 to -2, and then -1 to infinity. Yep. Okay. Where am I decreasing? So this means the graph is falling from left to right. Well, the first one's pretty easy to see. All right. And then the second one, I'm dropping from left to right. Okay. Now, typically that would cover everything, but there's a third possibility. I could be constant, which means my graph doesn't change its value, doesn't change its output. And it doesn't. Right here it is. Right? I have a horizontal line going straight across, not rising, not falling. I am dead still. So I have this broken up into three types of intervals. I have intervals where it's increasing, intervals where it's decreasing, and an interval where I'm constant. Now, how am I going to describe these mathematically? Okay. Well, I said this is increasing. Oh. I did not say that. It is constant. So this is decreasing. I said this is decreasing. And then I said this is increasing and this is increasing. Now, on the graph, and just conceptually, when we talk about a function is increasing, decreasing, or constant based on its y value, right? It's all about what is y doing, right? What is my function? What is the output doing? Is the output increasing as I move from left to right? Is it decreasing as I move from left to right? Or is it constant? So you would first think, oh, well, where am I increasing? I'm increasing from this little spot right here. This is from 2 to 3. Okay. Well, that's okay, except here from 3 to 2, I'm falling. And here from 2 to 3, I'm rising again. And from here from 3 to 2, I'm falling again. Yeah, so I can't describe increasing and decreasing as the y values that are happening. I have to describe them using a interval that only occurs once. We know this is a function. We know it passes the vertical line test, which means I can keep drawing vertical lines all I want. I'll never hit the function twice. That sounds like a great way to keep track of where am I increasing, decreasing, or constant. So where a function is increasing, decreasing, or constant is measured or shown by the x values. All right. So the y value is what tells me if I'm increasing, decreasing, or constant. The x value is tells me where it happened. So this first little bit of blue, this was constant. The ends don't have arrows on them, so that means it doesn't. This does not go on forever. So that means this function starts at the point, what is this, -8, 4, and then goes up, down until we get up here to whatever this value is up here. And I tell you what, let's make it go on forever because it just makes life easier. Okay, so if it goes on forever, I am constant from, where do I come from on the x-axis? Well, if I go to the left as far as I can, this is going to take me all the way out to -infinity. All right. And then what's the x value where the constant stops occurring? -6. Okay. What about the next break? All right. Well, where's my next change of behavior? Well, I went from -infinity to -6 where I'm constant. And then if I go from, I keep decreasing until it stops. What is my x value here? I'm just asking for the x value, not the y. X value there is -3, right? And then I start to increase until I stop increasing. Where does that happen? That's when x is -2. And then I start to decrease again. And then where does it stop? And x is -1. And then I start to increase again, and that goes on forever. That goes on until +infinity. Right? So you take her out. She's looking. All right, so I want to talk about where it's increasing, decreasing, constant. I need to use x values to do that. So what I can do is just throw these. I can look at this a couple ways. I can either kind of throw those highlights down on the x-axis. So I went from forever up to -6, and then I was decreasing from -6 to -3, and then I'm increasing from -3 to -2, and then I'm decreasing from -2 to -1, and then I'm increasing from -1 to +infinity. So when I write that out, what does it look like? Okay. Well, I'm increasing from, this is x is, increasing was the green. So I don't start increasing until I get to -3. And then I do that until I get to -2. I'm gonna put parentheses around that. That is not a point, that is an interval. Okay, this is x's from -3 to -2, and then I pick it up again on the other side of -1, and I go on forever. So there's the increasing. Am I decreasing? I'm decreasing from x is -6 to x is -3, and then I'm decreasing again from -2 to -1. And then where my constant? That starts all the way out at -infinity and goes until I get to -6. Okay. Now I want you to notice something here. And that is none of the intervals contain endpoints. Do you see that? None of these intervals contain endpoints. All of them are all of these intervals are always parentheses. And the reason for that is when I want to talk about a function increasing, I'm going to get you that formal definition down below so I can explain why this is. But they never contain the endpoints because when a function changes its behavior from, in this case, constant to decreasing, decreasing to increasing, increasing to decreasing, decreasing to increasing, whenever it changes its behavior, it's not doing one or the other. It's not increasing at that point, it's not decreasing at that point, it's not constant at that point. It actually can't be described as doing anything because it's a single point. To be increasing, decreasing, or constant, you have to be over some interval or some span, and the behavior has to be the same. All right. Now, next, the maximum value of the graph. All right. Well, that doesn't really work in this one because there is no maximum value because I go on forever. All right. So I don't have a big like global max, but I do have some relative maximums. I have some points that are higher than any of the points around it. And what are they? Well, from constant to decreasing, this isn't higher than any of these points. And then I'm dropping, that's not higher than any point around it. And then I rise, and then I stop here. That's a maximum, right? I have a maximum there. And what this is called is a relative maximum. All right, so I do have a relative max of, let's write it correctly. What's the y value right there? It's 3, relative max of 3 when x is -2. All right. Now, relative max just means it's a point higher than the points around it. It's kind of like in the Alps. You know, the top of the mountain is where that's where the peak is. That's where the edges meet. But if you keep going around, all of the mountains are tall. They all have a height. And then if you were out there and you saw Everest, or you saw Everest over toward Tibet, it would be the global max. It's the point, it's the value that's the y value that is higher than any other y value in the problem. This one doesn't have that, but it does have a relative max. Now notice the way I wrote this, okay? It says a relative max of 3 when x is -2. Okay. So this means the maximum occurs The maximum is the y value, and it occurs when x is -2. It's just like the increasing, decreasing, and constant. The y value's behavior is what determines it, but then the where did it happen, that always comes back to x. How about the minimum value? I have a couple of those. Okay. So here's a relative min, and it is 2 when x is -3. And then I have one down here as well. I have a minimum of -1 when, oh, Larry, a minimum of 1 when x is -1. Now, so I got two minimums. Everything else, there are no points nearby that make that do what is required. These 2 points are below all the points around them in an interval. And then the -1 is actually a special case because this is a global min, which means that is the lowest number this function returns at all, right? The function never returns anything less than -1. Okay, so I have a relative min and a global min. So let's see if we can cheat the system here. I got a relative min of 2 when x is -3. And I have a global min of -1 when x is, no, global min of 1 when x is -1. All right, let's jot that in here. And then next, at x is -3, a relative minimum occurs, and its value is 2. Based on that, can you identify the location and the value of the relative maximum on this graph? The answer there is none. Oh, sorry, relative max. Yeah, I can do a relative max. I can't do a global max. The relative max we already talked about is right there. All right, I have a relative max. The location, x is -2. The value is 3. All right. So this gets us into 1.7. We'll stop there on, let's see, next Tuesday. Go ahead and make sure you have the notes for 1.7 done or out so you can access them, because we will be getting through 1.7. It looks long, but each page only has 1 or 2 problems. We have an entire graph, so it just takes up a lot of space. So be prepared next time to tackle this. And then, so that means 1.7 on next Tuesday, hopefully end of 1.7 through 1.8 on Thursday, and then 1.8 review the next Tuesday, and then the test would be after that. So my thought right now is finish 1.7 on Tuesday, hopefully finish 1.7 and then finish 1.8 on Thursday. Open the test maybe the 24th if we have time for a review, and then it'll be due that last weekend in October. So 28th, 29th, 30th, 31st is when it'll be open. All right, the notes for 1.7. Oh, let's make sure they're there. Notes. Weekly lessons. Guided notes. Blank notes. Blank notes. Yeah, and that should be all of them. Yeah, so there's the 1.7 part 1, 1.7 part 2, and then 1.8, which is the last thing we'll cover. So when you go into the notes, click this top. It looks like it's a link, but it's a link to the folder that contains all the notes. All right. Great.